In this video, we're going to explore the idea of a doubly linked list. The idea of a doubly linked list is that rather than our node just holding a reference to the next thing in the list, what we do is we add a second property, which is called previous. And what previous does is it keeps track of the thing that came previous to this node. So we now have a pointer to the thing that comes next in our sequence, but also a thing that came before us in this sequence. And we'll see that this helps to improve the time complexity of some of our different linked list operations. So I set up our linked list so that it is the same as our singly linked node. I'm just going to show you how to modify it so that it works with the doubly linked list. And then we'll take a look at some of the things that change with that, right? So let's start off with insert front. Basically, all of our initializations stay the same because none of them make reference to any particular object. So the first change is our insert front. Basically, we have to make this so that it now has that previous value provided. The self.front, self.rear equals new node is still the same as usual. All we really have to do here is consider, well, what actually happens when we insert something to the front, right? The thing that used to be at the front needs to have a previous pointer to the thing that we're inserting, right? That would maintain the link for us. So what we do is we just say self.front.previous equals new node. So if we consider our chain of values, right? When I insert a value to the front here, say it's the value 0, basically there's a two-way pointer, right? That'd be the same here, right? So there's like a two-way pointer. 0 points to 1, and 1 points to 0, right? So it points in both directions. We have a pointer to the next node and a pointer to the one that came previous. So do you see that we're basically just maintaining that property by adding this line, right? That gives us still O of 1, so nothing really changed here. It's still a constant time operation, so this method is all good to go. Insert to the rear is very similar, right? We just add this none property for previous. This self.front, self.rear new node is all the same. Now I have to consider what happens when I add something to the actual rear, right? Well, what's going to end up happening is the value that I'm inserting needs to have a reference to the previous rear value. So what I do is I say new node.previous equals self.rear. There we go. That's all we really need to change here in order for this to work. We just have a pointer now to the previous rear value, still constant time. Everything's good to go. Now, insert will differ a little bit in the sense that I don't need to keep track of previous anymore. The reason I don't need to keep track of previous is because we now have a reference to that inside of our holder node. So what we could do is rather than saying previous, we just say holder.previous.next equals new node, right? And then for this insert as a part of it, right, when you consider the idea that we're inserting at a general index, basically what ends up happening is if I were to insert at index 1, the value 0, it needs to point to the value 2, and it also needs to point to the value 1, right? So it has to have these two-way pointers associated with it, right? So basically what ends up happening here is our new node has the value, it has the holder, and it's going to point previously to holder.previous, right? Then the holder's previous next value becomes our new node. And then there's one more update that we need to do here, which is holder.previous equals the new node. And that's how we do our insert now. So this just maintains that previous property and makes it so that we don't have to keep track of that previous node. This is like marginally more efficient in the way of memory storage, but it's not really a huge improvement. It's still going to be generally a linear time complexity, so nothing really too crazy is changing here, right? Now we could turn our attention to our deletes. When we take a look at our deletes, we have to consider, is anything really changing in these processes? If I remove the self.front, the main thing that's going to change here is that the self.front's previous should point to none now. Just that way we remove the link to self.front from the whole list itself, right? So that's the main thing that's going to change in this deletion. Now, delete rear is where we're going to see some real improvements, right? We can get rid of all of this. And basically all that happens is self.rear is going to be equal to self.rear.previous, right? It moves us back 1 from the rear, right? And then generally what we do here is we just do self.rear.next equals none to effectively remove the value. And then from here we could do self.size minus equals 1. this is the key improvement of the doubly linked list. This is now constant time. So this gives us a constant time deletion from the rear, which may be desirable depending on your particular use cases. So this is the main primary improvement that we have. And then just to finish things off with our deletion, right, what's going to end up happening is once we get to the end here, we don't need to keep track of previous anymore, right, because we already have a reference to it. This would be holder.previous.next equals holder.next. And then what we do is we do holder.previous equals holder.previous.previous. Right, so like if you're considering the way that this is looking, just so that you can see generally what this looks like, right? So if I have this sort of doubly linked structure, if I were to remove 2, right, what I'm saying is that 3's previous pointer needs to point past 2 to 1. So you see that it's the previous. Right, so that's why we have to go back to like that, right? So that's generally the way that this pointer is being updated here. And with that, that gives us our whole doubly linked list. You can see it's not too different from the singly linked list, and it gives us a bit more of a time complexity improvement for delete from the rear, which is a nice thing to have. Just to help demonstrate this, let's just go ahead and run our same examples. They should still run the exact same way, right? We'll just make sure that nothing fails. So you see here we have 142 because we deleted a value from our linked list, right? If I remove that deletion and just keep my insertions, I have 1432, which is exactly what I expect. One additional kind of fun idea here that I just want to show, another sort of little advantage of our linked list is that it's particularly easy to reverse. I could actually print it in reverse in a very easy way, right? So I could set up a pointer to self.rear, and then rather than doing holder.next, holder.previous. So you can see that we can actually print this in reverse very easily, right? You see we get 2, 3, 4, 1 instead of 1, 4, 3, 2. It's just completely in reverse. This idea of reversing a linked list is actually something that could come in handy if we wanted to reverse the ordering of something. So for instance, say you had something sorted in ascending order and you wanted to iterate it in descending order, being able to iterate it backwards might actually be an advantage to you in that sort of case, rather than having to reverse the linked list of a singly linked list, which is a problem that we'll look at in the next few videos, and you'll see that that actually is a fairly complex task compared to having a doubly linked list like this. So those are the main ideas of a doubly linked list. We have a linker to the previous of the node that we're currently at. And what that does for us is it helps to improve our delete rear, where we previously had to iterate, now we don't, we get a constant time operation. It also allows us to reverse our list if we wanted to do something like this. So thanks so much for watching this video, and I'll see you in the next one.